Hey everybody who's here watching right now. We are about to get started. If you are here, feel free to ask some questions. I've changed so many things. I was working on stuff this weekend, changing the colors and everything. Let's bring the game up. Oh, don't want to do that. Let's see right here. Doing some quick adjustments on everything. Let's see. Sure, we'll go with this right here. Wait, and then sure. This is what one of these days I'll make everything. No. One of these days I'll get everything standardized and it'll all be the same every class. But it's like the light changes in here, daytime, nighttime, everything changes, morning, it's all different. But with that, let's see right here. We've got the assignments up. I've got everything up for every class. If you are here from any class, let me know. I'm going to bring up 201's assignment too while we're also talking about this. So let's bring up 201's assignments. And let's see. No one's jumped in the chat yet. But let's bring up what 201 did here. 201's assignments. They've got some tricky stuff coming up. So I might take a look. If you're 320, if you're 474, let me know if you're here. Say hey in the chat. Hey, what's up, Dan? What are you working on, Dan? I'm going to probably pull up some 201 work, but whatever you're working on, let me know. And I'm pulling up the 201 assignments as we speak. I've got everything else open. Okay, 201, I've got the homework 12 open. I've got homework 12 open. So chapter 12, are you doing quiz or homework? Are you doing quiz or homework? I've got the homework open right now. Here, I can hop over to that. So let's see. Let's hop over to the homework. Let's do this. Hey, it's the randomness, everything. I got every button clicked. Do you want to talk about which quiz question are you doing? Hey, what's up, Jake? 4B on 474 asks how to describe the clusters that differ. Does it want us to just describe? Yeah, it says describe, I think, 2 cluster centers that are different. So I can hop over to that one real quick. So it says talk about 2 cluster centers that are different and in what ways. Are the numbers off? Here we go. Oh, I was like, what's going on? That's 320's homework. So we go all the way back here, back. And here you are right here. Describe 2 cluster centers that differ from each other. So basically, this is where we're talking about our top customers, different degrees of customers, and what ways can we describe them that would make sense. So think about, your top customers, your average customers. What ways are these cluster centers different right here? When we talk about this, I think Kroger data we're working with right here. What ways in their buying habits are different? Like, what are their different buying habits? And how could you differentiate between these 2 clusters? Because that's what really gets into, with clusters, we want to have a scheme for the differences between the clusters and say, this cluster is going to be our top clients. This cluster is going to be our clients that we're probably losing. Does that make sense, Jake? So to do the comparisons, we actually need to look at the centers of the clusters. And right here, we're looking at the z-scores. So when we look at this, we can kind of talk about, we won't do it in context yet, but we can talk about if they're buying more or less. And I believe these items for the Kroger data set is like milk and all that good stuff. So if we look at, there's survey 09. So wait, are we not doing the Kroger? Maybe we changed it. Talking about the differences between the students now. So here we are. So here are the differences. Oh my gosh, they look so crazy today. So here's the differences between them. And definitely, well, this is just the characteristics right here. But here's the variables you'll be looking at. This semester, it's not the Kroger data. We'll look at Kroger data here soon. But you're looking at weight, GPA, weekly hours study, Facebook friends, text. And these are not the clusters themselves, but we need to turn them into clusters. And I don't want to do it all yet. Question 3, what does the question say, Dan? Because it might be different for me. But does this make sense, Jake, that you're going to have 2 clusters that you're going to differentiate between, and looking at where the z-scores are for these clusters? You can talk about this one's a little bit above average in this one's a little bit below average in this one's about average in this. And so the z-scores are going to be the key for differentiating between the clusters. So does that make sense, Jake, that you want to then make comparisons of the clusters? Yep. And then just kind of 2 clusters that really have a good differentiation between them. And of course, this has not been standardized yet. I think we did the standardization of it last time. Probably the quickest way, after scaling, you should... So the quickest way to scale this is going to be... So we got the scaled data right here. The one talks about cars, and if they get in yes. Is it 2 cars or 1 car? Let's do that one here next. So does it want us to do a for loop? Yeah, just a singular for loop, right? And I in vector. We did this one in class. 1 through the number of columns of this right here. And then we'll go from this and we'll insert into it. I think we just say scale. That should work. Scale this column. Wait, that's a row. We don't want to scale the rows. We want to scale the columns. That should do it. Looks good. Run a summary, and everything does look to have the right values because everything has a mean of 0 and it looks to have a standard deviation of 1. So that's how we can scale the values right there to get everything on the same playing field, and then we can run some k-means algorithms on it, and we can run the hierarchical clustering. Let's take a look here at the two-car pair one. So let me get the quiz question up. Chapter 12 quiz. 2 cars are going to be repaired. Okay. So there's a lot of questions here. I will find it in just a moment. So 2-car repair problem. 2-car. Was it this one? Nope. That's not it. Oh, is it this one? It might be the other one. No, it's not this one because this is this one. No, I think it's this one. We'll do both of these. Why not do both of these? Okay, let's check it out. So here are the questions. We'll do both of these right here. A consumer organization estimates that over a 1-year period, 18% of cars will need to be repaired once. 16% of cars will need to be repaired. Oh my gosh. 18% of cars will need to be repaired once. 6% of cars will need to be repaired twice. And 1% of cars will need 3 or more repairs. So they left something out here. They left out the cars that need 0 repairs. And so let's write this all down. We're going to bring up a small word sheet that we can keep on the screen right here. Okay. So we're going to have the word pad right here to help us out. And let's take a look. The first question we can work on. Let me bring up my screen right here so I can see everything. Okay, it says a car needs 1 repair 18% of the time. So let's go to draw. And let's put probability of 1 equals 18%. The probability of 2 repairs equals 6%. The probability of 3 or more repairs is equal to 1%. And that would put the probability of 0 repairs is going to be 75%. And the way we obtain this right here is that everything here needs to equal up to 1. So when you look at all the probabilities, they must add up to 1. So the sum of all the probabilities has to equal to 1. And as long as I'm doing the math correctly, we obtain 100% right here. So just to check, we can take 18 plus 6 plus 1 is 25%. And that's where we get the 75, which is 100%. So we've labeled out all the probabilities right here. This is what we call the sample space. So the sample space is everything that can occur or like could occur when we sample. The car can need 0 repairs, 1 repair, 2 repairs, or 3 or more repairs. If you notice, I'm also saying or, meaning that these are disjoint probabilities because we're going to add them up. I'm saying this could happen, or this could happen, or this could happen. So what is the probability that the car needs no repairs? 75%. What is the probability that a car will need no more than 1 repair? Now this one's tricky the way it's worded. When they say no more than 1 repair, they're saying 0 or 1 repair. And the key word right here is or. When we say or, what will we do with probabilities, Dan? When we say or, what will we do with probabilities? So if I say, what's the probability that it needs 0 repairs or 1 repair? And that's a key word to know. And we need to remember that they will be disjoint. We'll add them together. Bingo. So this will be 94%. We will add them together. What is the probability that the car will need some repairs? This is the complement of not needing repairs. Either the car needs repairs or it does not need repairs. So if the car does need repairs, it would be this right here, which is going to be 1 minus 75. So this right here, oh, MuBot's not on. Let me get MuBot going right here. Sorry about that. I forgot. New week. MuBot's crashing the stream right there. Sorry about that. MuBot will load up in the background right here. I totally forgot about I'm sorry, MuBot. MuBot, don't be mad at me, MuBot. Oh my gosh, what did I do? What did I do? The probability that the car will need no more than 1 repair. That looks like the one I got wrong. What did I do? The probability that the car will require some repair. I hitting up my probabilities wrong? I've seen one time where the questions were wrong. Oh my gosh. I can't add. That was the only one I thought I got wrong. Yeah. It's just because I can't add. It was 6% and 1%, and I totally forgot about this 1% right here, and I put 94. I just looked at the 6. Sorry about that. That is just a math error, which happens to all of us. But the second one right here is the probability that the car needs no more than one repair would be these two probabilities added together right here, or basically not these two probabilities. So am I blocking that? Let me find out. It's blocking my way. Nope, not blocking that. So that is the probability right there. Just make sure you don't make the mistake I did. I think the next one's the more difficult one. This one's the one that tricks people right here. This one's very similar, but also very different. Let's put out our little cheat sheet right here, and let's change the probabilities. Okay. And let's see how this problem is different, because this time you have two cars, and that's what's different about this problem. So it says the probability that a car will need to be repaired once is 17%. The probability that a car needs to be repaired twice is 6%. The probability that a car needs 3 or more repairs is 3%. And that means the probability up here is 74%. So we can double check. We're always going to double check our math right here to make sure we did it correctly. 74 plus 17 plus 6 plus 3 is 100%, and there is the probability we're looking for. This is now the sample space of everything that can occur. And now we get to the harder questions, the probability that neither car will need repair. So tell me about this. Your first car did not need repairs, and what about your second car? Your first car did not need repairs. If you're here right now learning this, this is going to be a major part of today's lecture. Your first car did not need repairs. What about your second car? For the question number A, your first car, and good to see you here, Charlie. Your first car did not need repairs, and what about your second car? Your first car did not need repairs, and what about your second car? Your first car did not need repairs. What about the second car? I think, Charlie, I think you're doing it. I think that sounds about right. Is that going to be right? I'm trying to think. 9/16 I think is the answer. Very close to 9/16. Is that 9/16? I think that sounds about right. Because what it is your first car did not need repairs and your second car did not need any repairs. So actually, if we put probability of 0 times probability of 0, that would make more sense. So the probability of 0 times the probability of 0. Because your first car did not need repairs and your second car did not need repairs. And this is key right here. Yeah, that's exactly right. And that's what I've written right here is your first car did not need repairs and your second car did not need repairs. So you just multiply the two probabilities together because they're saying it's independent, which is one of the assumptions about this problem, that your car needing repairs is independent of your other car needing repairs. So we will assume that that is true. We might be wrong. So there it is. Your first car did not need repairs and your second car did not need repairs. The probability that both will need repairs is what? So what is, and then you might have this one, it looks like, Charlie, because now what we're doing here is we're saying your first car needed repairs and your second car needed repairs. So the probability that your car needs any sort of repair is going to be here. And this is equal to, so this is probability of repair, let's put it this way. And probability of repair is 26%. So the probability of any sort of repair is 26%. So either 74% probability your car does not need repairs, 26% probability your car needs some sort of repair, 1 repair, 2 repairs, or 3+ repairs. Now we're going to look at your first car needed a repair and your second car needed a repair. So this is a independent probability right here, assumptions. Oh, no worries, Dan. Do you see what we're doing right now? We just did the other one. I made a mistake. I did wrong math. We got it fixed. But no worries. We're working. If you have questions, feel free to ask. We're just showing how to write down all the probabilities and then solving for both your cars need repairs. And then the math is going to be 0.26 times 0.26. So we just go here and do 0.26 times 0.26, and that's the probability there. And then the last one seems confusing. But there's two scenarios. Either none of your cars need repairs or at least one of your cars need repairs. So either none of your cars need repairs or at least one of your cars need repairs. And probably the best way is going to be to write this out right here and show it, that when we have this, we have a few possibilities. We have no repairs no repair. And this is your car. Your first car did not need repairs. Your second car did not need repairs this year. Your first car needed repairs. Your second car did not need repairs. Your first car did not need repairs. Your second car did need repairs. And repair. Now, we want to see the probability that at least one of your cars needed repairs. So we want this. I think, Charlie, yeah, you got it, Charlie. Because this one right here was the very first thing we figured out. And this probability right here is equal to 0.5476. And that's because no repair times no repair. It was 0.74 times 0.74. That's how we obtained that number. It's no repair. It's the very first one we did if you review back. So it's no repair times no repair. And then what are we doing? Right here, what do all of these probabilities equal up to, Charlie? If we add up all these probabilities, what do all of these, and great work, Charlie, this is what we're learning today, and you got it down. What do all these probabilities add up to right here? Boom, that's 1. So then what we're going to do is we're going to subtract off that one we don't care about to find the remaining ones, because we're literally just going to take this out of it, and we'll have the remaining probabilities of these 3 right here. Because either none of your cars need repairs, or at least one of your cars need repair. If you notice, we just said the complement rule right there because we could add these. You could add these probabilities right here and get 1. So we literally know the mathematical equation here. I'll enhance this a little bit more. We know the mathematical equation that 1 is equal to 0 repairs plus the probability of 0 repairs plus 1 or more repairs. So if you look, 1 or more is right here, and we could just call this y, and this is x, and that's x right there. So we can solve it out. I hope that makes sense to everybody. I've done a lot of scribbling today. I have just been getting over them kind of by trial and error. I don't know the official formulas yet. Yeah, no, it's you just have to know the terminology. And oh yeah, you were messaging me about this, Charlie. Great work. You said you were working on it, and you're getting over it. You're doing a great job. Yeah, once you figure it out, it's like, okay, I get what's going on. And then I hope today it makes a lot more sense as we're talking through it. I remember we were talking on Discord, and you were saying, I'm just practicing up, getting ready for today. And I'm like, I thought, that's awesome. Yay, we got 100 on that one. That's one of the harder ones. Here, wait, there's a really tough one people think. Is it this one? No, it's not that bad. There's a really tough one. Yeah, here it is. You purchase, it's not really tough. Once you know how to do it, it's not that bad. You purchase a 5-pack of light bulbs that were recalled because 14% of the lights did not work. Once you hear that, you should immediately go to your sheet of paper and take some notation. So you should go here, and you should write down probability of broken. Let's put probability broken right here. Probability of broken equals to 14%. The probability of a good light bulb is equal to 86%. So we have the probabilities written down instantaneously. So let's see what the question wants us to do. What is the probability that at least one of your light bulbs is defective? At least one of your light bulbs is defective. So what I do for these problems is I make a number line. Let's do this. I can't get around it. No. Oh, look at that. There we go. I'm going to make a number line right here, and we want to see at least one of our light bulbs is defective. So when you think about it, here's what could happen. Here's all the light bulbs we could get, and we want to look at the probability at least one light bulb is defective. So that might be it. That very well might be it. Great work, Charlie. If you got it, this is a tough one for people. So we want to see this right here, and we don't want to see this. I think my pens might be working again. I'm scared to change them back. So we don't want to see 0 light bulbs defective. So Charlie, once again, what is the probability of all of this right here? What's the probability of every single thing I've put my bar underneath right there? What is the probability of all of this? 1. And so this right here has a probability of 1. And then this is the probability of 0 defective. So probability of 0 defective would be what? If no light bulbs were defective, then what would all the light bulbs be? If no light bulbs were defective, what would all the light bulbs be? If no light bulbs were defective, then all light bulbs would be what? If no light bulbs were defective, then all light bulbs would be what? So if no light bulbs are defective, we buy 5 light bulbs working exactly. They'd all be good. So I think you're probably doing this. I'll look over your math in a second right here. But this is literally the probability all good because there's 0 defective. So this is the probability all good light bulbs. So think about this. We want to solve for this portion over here. So we just want to subtract off this all good. So we want to do 1 minus the probability all good. This is the complement because if they're not all good, because this might as well be read everything but they're all good. Everything but they're all good would mean at least one is bad. Does that make sense, Charlie? So everything but they're all good means at least one is bad. So everything but all the light bulbs are good means at least one light bulb is bad. So either they're all good or at least one is bad. And then we have this probability right here that we found. So now we just have to put in the mathematical equation. So we do 1 minus, and the probability they're all good would be 0.86 to the 5th power. And that's because the first is good, the second is good, and the third is good, and the fourth is good, and the fifth is good. And that's the multiplication rule right there where you multiply all together. So we've kind of converted this into a formula now by saying, well, it's everything but all the light bulbs are good. And then we have the probability associated right there, and we can find it. But that's got it. This is one of the more difficult problems. If you get this problem down, you're really good because we ask if 1 or 2 like this on the test. Usually at least 1. Okay, I think that's right. So much easier on a TI. Charlie got it. Charlie said the answer right there. Amazing work, Charlie. Did it? Yeah, you got this down. Yeah, I think you rounded and everything. Great, Charlie. You were quick on that. Amazing work, Charlie. Yeah, and if you just practice the theory, so wow, you just did pretty much one of the toughest problems we have in this chapter. You just destroyed it, decimated it. Great job. For a sales promotion, the manufacturer places winning symbols under the caps of 19% of soda bottles. If you buy a 6-pack of soda, yeah, that one's it is a tough one. It's one of those ones you got to practice and know how to do. But this one, look at this. If you buy a 6-pack of soda, what's the probability that you win something? What would we not be interested in? So let's go back to here. We have 19% probability of winner. So we can just change our problem here. So we could go back to here and put probability of winning, probability of losing, and probability of winning is 19%. And we want to see the probability you win something, right? So if we want to look at the probability you win something, it'd be everything but all the bottle caps you get are what? It'd be everything but all the bottle, and there's 6 bottle caps this time. Well, we can basically keep this the same. It'd be everything but all the bottle caps are what? If we want to say, yep. So we want to find out the probability of 0 winners, which would be all losers. So we can highlight this here. So 0 winners would be all losers. Oh, that's one we're not interested in. We don't want to see you get 0 winners. We want to see at least 1 winner. So this is at least 1 winner. So we want to do 1 minus prob all losers. What's the probability of all losers? What's the probability the first bottle cap is a loser, the second bottle cap is a loser, the third, the fourth, the fifth, the sixth bottle caps are all losers. And this is not how many things you open, it's how many winners you get. So we're seeing you get at least 1 winner in this set of points right here. Yep, the probability of a loser is that. And then how do we do? You get 6 losers in a row. Well, to do the probability of a recurring event that's independent of other events, we multiply it. And all we're doing, this is shorthand right here if you're wondering. This is shorthand for 0.81 times 0.81 times 0.81 times 0.81 times 0.81 times 0.81. So that's how we're just doing it pretty quickly right there to get the probability of, oh no, wait, did I do it right? Yeah, I did it right. Yeah. I think, oh, and then Charlie, you found the answer right. It was so close to 0.81 that I was like, wait, did I do it wrong? But I got a little bit afraid there. I was like, no, I can't make a second mistake today. They'll say, Brian, you can't teach anymore. You get 1 mistake a day, they say. It's UT's policy. 2, 3, 4, 5, 6. So it keeps multiplying when I do that. We do 1 minus, and we confirm we got Charlie's answers. Oh my gosh, what did I do? 0.81 times 1, 2, 3, 4, 5, 6. Copy, 1 minus, paste. There it is right there, 718. I was like copy pasting and then kind of deleting decimals. Oh my gosh. I didn't copy paste the right answer. There we go. That's got it. That's done it. Wait, oh wait, that's the last question. No. Your list of favorite songs contains 3 rock songs, 9 rap songs, and 4 country songs. What is the probability that a randomly played song is a rap song? Well, it's just probability out of it. It's just how many there are. So let's figure out how many there are. There are 3 plus 9 plus 4, and you have 16. And you're looking for a rap song. So 9 rap songs. We should be able to figure this out in our heads. So that should be 56.25. Yep, there we go. Nice job, Charlie, right there. 56.25. Type in, and then what's the probability that the song is not country? And so people are wondering, it was 9 divided by 16. It was 9 by 16. Was probably the randomly played song is not country. So then this is going to be 4/16 or 1/4. It's because think about this. I'll explain real quickly. So I did in my head. What is a quarter? Like this one right here is a quarter of the songs are country, right? So a quarter of the songs are country. Does that make sense? So a quarter of the songs are country. So then what would this answer be down here? Because it's the complement. And I'll explain how I got the last one because you'll see, hopefully it'll make sense how I did the fraction in my head. So this one is going to be 75%, right? Because either the song is country or not country. And since 4 out of 16 are country, and then 1 minus is the remainder, or the complement of it, I should say. Now, the way I did the last one in my head is, think about this. A quarter is 1/4. So then what is 1/8? So do this real quick, Charlie. What is 1/8? What is 1/8? 1/8 would not be a quarter. It'd be a half of a quarter, which is a what? 1/8 is a half of a quarter, which is what? In decimal format, what would be 1/8? Because a quarter is 0.25, but 1/8 is a half of a quarter. Bingo. And then what is 1/16? So 1/16 is a half of an eighth. So what is 1/16? 1/16 is a half of an eighth. So what would that be? So we have to like move the decimals and you have to be a little bit careful. So you have 12.5 cents. Bingo. And then if you think about it, what you have if you break down the fraction is you have 8/16 plus 1/16. And so 8/16 is 1/2, which is 50%. And then 1/16 is 0.0625. So I was just thinking, I was like, what is 1/16? Because I know 8/16 is a half. And then I just added to the half the 1/16. Yep. So that's how that's what I was thinking when I was going through my head. I was like, okay, it's a half plus 1/16. And so I was like, 1/16 is 12.5, 6.25. Okay, 56.25. Yep. So it's just practice. It's just practice. I do math all day, so I'm lucky in that regard. So big brain. Thank you for the compliment. Some classic. I like that meme a lot. That meme cracked me up. I don't think people. It's meant to be more like like jokey. Yeah, like yeah. I always saw people talking about playing Minecraft. I'd watch people playing Minecraft making that joke. This one right here can be deceptively difficult. I don't think people understand what the questions are asking, and it's on the homework too. So when you look at this one, it's talking about the sample space, and the sample space is everything that can occur. So when you flip a coin, and you're going to, doesn't this one have rules? Toss 2 coins, record the orders of the heads and the tails. So if you toss 2 coins, and you just look to see if it's heads, tails, heads, or whatever, what 4 things can occur? And just, if you take 2 coins, just keep dropping them. Well, this one is missing one of the 2. If the outcomes are evenly distributed. So this one's this, and let's do the homework version of it, because then I'm not gonna make any mistakes, but you never know. Big brain. Let me go over to the homework version. The homework version, you get to see what you get wrong if you get something wrong. So, okay. So we're going to record the 2 coin flips. So we're going to record either it's heads, tails, heads, tails, heads, heads. And those are the sample space of everything that can occur. So when we say the sample space right here, we're talking about all the things that can occur, and here's all the possibilities that can occur. Now, when we ask, are they equally likely? So, Charlie, what's the probability of flipping a heads? What's the probability if I take a coin and I flip it? What's the probability I get heads? And thank you for being here, Charlie. I don't know if Dan's still here. Dan, feel free to say hey. Well, what's the probability? What's the probability of just getting heads on any random coin flip? Flip a coin. What's the probability you get heads? 50-50 on a perfect coin. So we will assume perfect coin. We will assume perfect coin, which is a good assumption, right? And I think they've shown like most coins are like 49-51. I don't know. I don't know how you could possibly. You'd have to do a lot of trials. Even then, it would be an estimate. And I guess at some point anyways. Enough stat talk. Let's go back to this stat talk. So what's the probability of getting heads? What's the probability of getting heads and then getting heads again? Like what's the probability of getting heads and then getting heads again? It'd be heads times heads equals to 0.25. So isn't tails just likely as every time you flip the coins, getting tails would be just as it's not talking about this sequence right here. It's not talking about getting the sequence heads, tails, heads, tails. It's saying these are all the possible outcomes. Does this make sense, Charlie? This is saying when you flip a coin, the only things that could possibly occur are two heads, tails, heads, or tails. This is everything that could occur. Yep. Now, what if I told you the sequence of events is this? Now, be careful. You could get, let's say here, heads, tails, or heads or tails. Like you could get one heads, one tails. Would those be equally likely if we list it that way? Like, or I'd have to say two heads, one heads, one tails, or two tails. Would these be equally likely right here? And why not? And the answer is no, they're not equally likely. If I list them this way as the outcome of this sample space, I could say when you flip two coins, you could get two heads, two tails, or a heads and a tails. Now, why would those not be equally likely listed that way? Think about the most probable one. Because you could get... So here's kind of the hint. Let me show a hint. If you list it that way, what is the probability of... It'd be 50%. 50% of the time you'll get one heads and one tails. 25% of the time you'll get heads. 25% of the time you'll get tails. Well, no, every single one of these is equally likely because here I'll write it in the chat so you can see. Heads times heads equals 25% of the time. Tails times heads equals 25% of the time. Heads times tails equals 25% of the time. Because oh gosh, take that back. Oh my gosh, I can't type today. Heads times tails equals 25% of the time. And tails times tails equals 25% of the time. And this is the percent of time you would get tails. But it's saying a new flip for each sequence. It wouldn't be 50-50, so head says the same as... I'm slightly confused here. I think you and I have a I'm sorry, Charlie. I'm trying to figure out where the disconnect is. But if it says a new flip for each sequence... No, well, so theoretically what we're doing right here is we're picking up coins and we're just dropping them and we're seeing what we get. It's saying, why is heads 25%? Because you're doing 50% times 50% right here. And so it's saying, like, if you have two coins, the probability that you will get heads and heads when you take the coins and drop them is 25%, because the probability one of the coins will be heads is 50%, and the probability the other coin will be heads is 50%. So it's 50% times 50%. So that's a 25% probability. Does that make sense? So it's the independence rule that the first coin is independent of the second coin. So the probability the first coin is heads is 50%. So does it make sense what it's asking? I think there might be a disconnect on what it's asking. So it's kind of like we're just listing it out and saying, I'm trying to think if I can... Let me think of it this way. Here, imagine this. Here we can... So here, but think about it this way. I'll do a more difficult version of it. It might make sense. Okay, let's take 3 coins. Let's take 3 coins and think about all the combinations that could occur if we have 3 coins. So let's go right here and start listing out. I think it would be, right? It would be. Every combination would have a 1/8 probability. Yeah, exactly. So if you did, great minds, Charlie. See, big brain, both big brains. So this will take a moment to list out. And then my brain is just slowing down. I had the big brain moment and then it went away. Okay. That last T almost looks like an H. Okay. So here is every possible occurrence with 3 coins. With 3 coins, you could get tails, 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 mega brains, mega brains on Monday. You could get tails, 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 heads, 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 tails, heads, heads. This is all the combinations of things that could occur. But what is the probability that a singular coin, with my horrible handwriting, what's the probability of just getting heads when you drop the 1 coin? What's the probability of just getting heads when you drop the 1 coin? Like just dropping 1 coin, what's the probability it's heads? 50%. So this is where the probabilities come from right here of 50% times, gotta go way smaller than that. So 50% times 50% times 50%. So, and these are all associated with these right here, because what's the probability that the first coin is heads and the second coin is tails and the third coin is tails? And that's where we'd get the probability of 0.125. And that's just multiplying these through. Now, every single one of these, by virtue of being heads and tails, will all have the same probability because they're all 50% probabilities. Oh, so yeah, exactly. It's just as likely to get heads, tails, tails as tails, tails, tails. But if you talk about it differently and you say 2 heads, the probability of 2 heads would be 0.375 because I'm just adding these together because they're all 0.125. So the probability, it just depends on how you talk about it. I'm going to write this down pretty nice. So each of those have their own probability of 0.125, but the probability of 2 heads is 0.375 because you would add those together. So you can add those up to get the probability of multiple events occurring. So you could say, what is the probability of at least 1 heads? What is the probability of at least 1 heads right here, Charlie? So looking at this sample space, yeah, no good. I thought this might help seeing it this way. What is the probability of at least 1 heads? What is the probability of at least 1 heads? And here's the answer. It's really easy to do if you look at it this way. It would sound like a really hard test question, but now the answer should be very visible. If we say, what's the probability of at least 1 heads? So, yep, bingo, that's it. Yeah, because you can see all the probabilities are equally likely. 7 out of the 8 probabilities meet the condition. So there you go. Great job. I might do it as 1 minus 1/8, but I'm overcomplicating it. But yeah, so you're doing a great job. That's the complement rule right there, or we're just talking about probabilities and sample spaces. But no, excellent work, Charlie. A really good review. You're gonna know this stuff super well today. So they're all equally likely because they're all 50-50. Gotta watch out. It'll switch the yes and no place. A family has 3 children. Record the number of boys. Exactly, Charlie. Great work. And so we're going to record the number of boys in a family. We're going to look at, let's say boy, girl, then 50-50 shot of boy, girl. But think about this. Yep, you're right. You can have 0 boys, 1 boys, 2 boys, or 3 boys in a family. And now here's the thing for equally likely. Let's say a family were to have 20 children. What do you think is the most likely amount of boys for the family to have if they have 20 children? Like if this was 20 kids that a family has and it goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to 20, what would be 10? You're right. So it's kind of towards the middle, right? 10 would probably be the most likely amount or near the most likely amount. I can actually show you the distribution of that. Why not? Let's go show the distribution of that real quick. So if we had a 50-50 shot, binomial applet, Iowa. So if there was a 50-50 shot of a family having a boy or girl, I'm going to totally lose the applet. Then we'd go over here and we'd put in 3 trials and we'd go to 50%. And there's the probabilities right there. And it's actually very similar to what we were just doing. If they had 20 kids, which I said theoretically, here's the simulation right here, but love applets, makes it so easy. And you know what's funny? This is literally the problem we just worked, Charlie, a moment ago. If you look at all these probabilities, it's the same probabilities, but with 3 kids, we could just change this to boys and girls, and you can see the possibilities right here. So it's the same probabilities. Sorry about that, everybody. I think I had a sneeze button. So these are the 1/8s, these are the 3/8s, and these are the 1/8s. And you could just change those to boys and girls instead of heads and tails. But does that make sense, Charlie, right there? Thank you so much, Dana. Thank you. I appreciate that. It's like, what are you supposed to do? Anyways. If you can, exactly. It's more likely you'll kind of have a half, and these could just be boys and girls right here. So as long as everyone understands like boy, 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 girl, girl, boy, girl, boy. So the probabilities right here show us that they would not be even probabilities because it's more likely you'll have, as Charlie said, there are 50-50. So these probabilities are not equally likely. Nope, not equally likely. Flip a coin until you get a tail or 3 consecutive heads. Now, I want you to think about this real briefly. You're going to flip the coin until you get a tails or 3 heads in a row. So what immediately is the probability of... Well, that's the answer. Charlie, you are right. That's the answer. And what's the probability of getting tails on your first coin flip? What's the probability of getting tails on your first... Like, just think. Just don't think too hard about it. Well, you flip. What's the probability you get tails? Boom. So there's 4 probabilities on here. And the sample space has to add up to what? The sample space of events has to add up to a probability of what? Like if we talk about everything that could occur, the sample space must add up to what? It's everything that could occur, which would not overlap in what occurs. But if we talk about everything that could occur, the sample space has a probability of, so it's everything that could occur. And we talk about this has a possibility of this has a possibility of this. So the sample space has a probability of 1. The sample space has a probability of 1 because it's everything that could occur. So we'd be saying, here's the probabilities of everything that can occur. And they would all add up to 1 if you said, well, this could occur, or this could occur, or this could occur, or this could occur. Does that make sense, Charlie, right there? And why is it this one? Because you're going to flip until you get 3 heads, or you get a singular tails. So you could flip and get tails right away and stop, or you could flip and get heads and tails and stop on the tails. You could get heads, tails, and stop, and you could get heads, and stop. More specifically, we can just see right here the sample space has a probability of 1. Let's just grab this. I don't know why I'm copying it when I can rewrite it. And let's enhance. So, you're welcome, Dana. I'm so glad they're helping out. I want people to understand these concepts more and want people to do really well on the test. We have people get hundreds on the test. I'm really, really proud of that. I don't know if I could get hundreds on the test because I make mistakes. People are better than me. They don't make mistakes. So there's that one. This one would be 0.50 to the second power because it's 0.5 times 0.5. Let's write that one out. It's 0.5 times 0.5. So 0.5 times 0.5. And this one is 0.50 to the third power, 0.50 to the third power. This is still a third power because we're still just multiplying all these 0.5s together. It's just 0.5 times 0.5 times 0.5. So if you were to add up all of these right here, what would you get? And we can show it. Well, because this is 50%, this is 25%, this is 1.25, and this is 1.25. So if you add up all these, what do you get? You get 1. Because this is the sample space, and it's every... Boom, Charlie, you got it. That's got it. So... And are they equally likely? Nope, they're not equally likely. So that's the main thing we're looking for. They are not equally likely. What am I doing? Gonna get a wrong answer because I misclick. Not fair. They are not equally likely. Now the next one, it says roll 2 dice and record the larger number. So think about this. Let's just say we theoretically roll 2 dice in our heads and we roll a 1 and a 1. What would we record if we roll a 1 and a 1? What number would we write down if we roll a 1 and then a 1 again? We just take 2 dice, we roll a 1 and a 1. What do we record? We record A, the right answer. Yep. Because those are all the numbers that are on a dice. And I chose 1 and 1 for a specific reason. 0 is impossible. Bingo. And so these are just the numbers on a dice. We'll record one of those numbers. And I chose 1 and 1 for a reason because we're going to record the larger number. So what would you record if you rolled a 1 and a 1? What number would you record? You roll 2 dice and you write down the larger number. Let's write it down right here. Let's make everyone see it. If we're going to roll 2 dice and record the larger number, we'd record 1 if we roll a 1 and a 1. So let's put 1 and 1 right here, and we'd record 1. How about if we roll a 1 and a 6? How about a 2 and a 6? A 6 and a 6? A 6 and a 3? Now, what number will we record for all of these examples below? In the 2 dice rolls, we're going to record the larger of the 2 numbers. So in the 2 dice rolls, we're going to record the larger of the 2 numbers. So this first one, we record 1 because that's the larger of the 2 numbers. It's tie. But in all the later examples, what do we record for the larger of the 2 dice rolls? 6, you're right. And so what number looks to be very hard to record? What number, since we're always taking the larger of the 2 dice rolls, what number would be very hard to record if we're going to take the larger of 2 dice rolls? 1, because the only way to record 1, and I chose that for an example, is to roll a 1 and a 1. What number is going to be the most likely number to record? Because all we need to do is roll 1 of it, and then it doesn't matter what the other dice roll is. What's going to be the most likely number to record? So the least likely is 1, and the most likely, anything greater than 1 is more likely, yep, and then 6 is the most likely, because if you roll a 6, then that's the number you're recording no matter what the other number is. So once you roll a 6, if you roll a 6 to start, you can just be like, well, guess we're recording 6, because it doesn't matter what the next number is, because I can roll a 6 and then a 2, a 1, a 3, a 4, a 5, a 6, whatever. I'll record a 6. So are these equally likely? Is it equally likely you'll record a 1, 2, 3, 4, 5, 6? Exactly. I think you're seeing it, Charlie. And they're not equally likely. The most likely numbers to record are the larger numbers. The least likely numbers to record are the smaller numbers. They are not equally likely. Whoa, we just did 40% of the assignment. We might be able to finish the homework today. Let's try to do the homework. And we can just review. For something to be a valid probability table, you must have all the probabilities add up to 1, and all probabilities must be contained between 0 and 1. I think that's got it. The sum of all probabilities adds up to 1, and all probabilities are contained between 0 and 1. So you can see right here, you got 20%, 40%, 80%, and 100%. So since each probability is between 0 and 1, and the probabilities add up to 1, it is valid. How about this next one? If you think about what this would look like, red, yellow, green, blue, it's just a wheel in quarters. Just imagine this wheel, because it's saying to you a theoretical color wheel that'd be put into... Good talking to you, Charlie. Anytime, man. Great work today. Glad this helped out. You've got a great understanding right now. You're doing an excellent job, so keep up the great work. If we're looking at what this wheel would look like, it would look like this. My horrible drawing skills are going to come into play right here. Here's green, blue, and yellow. So this wheel would be a 25, 25, 25% wheel, which is 100% theoretically possible. And so we got this, and this is very possible. This wheel right here instantaneously has numbers greater than 1 and outside of 0, so definitely not possible. So at least 1 is not between. It is not possible. What would this wheel look like? It's 100% blue. That's possible. Just so you can see theoretically what it looks like. This wheel is literally just a wheel that is completely blue. It's a blue wheel. That's all it is, and that is totally possible. It's just saying that if you spin the wheel, you will get a blue spin. The next spin right here is 20%, 40%, 80%, 140%. So definitely not possible. Sum of all probabilities is greater than 1 is not possible. There we go. Suppose that 58% of families living in a certain country own a computer and 26% own an HD TV. I swear more than that now. These questions, they go outdated so quickly. The addition rule might suggest that 84% of families either own this or this. What is wrong? So when you think about this, let's change the probabilities. If you change the probabilities to the probability of owning a computer, let's do this. The probability of owning a computer is nowadays 80% for a family, and the probability of, let's say the probability of a HD TV is 70%, maybe something like that. Then if we add together these two probabilities, what would we get? We'd get 150%. And the issue is that there's overlap. The people who own a computer might also own a TV. So we'd have to actually, if we did this correctly, subtract off one instance of the intersection when adding them. You'd have to subtract off. We don't do that in this class. It's not complicated, but it's the probability of A plus the probability of B minus the intersection of A and B. So you don't add up the intersection twice. So you could actually add up the probabilities here and get the following answer. We don't do that in this class though, but the answer would be that. If you add them up and you double add them up, you add up this area twice, and that's where you get the extra add-on to it. So the answer is not going to be adding them together because there's overlap, and the question should illustrate that. A family may own both a computer and a TV. These events are not disjoint, the exact word we want to use. So the addition rule does not apply. Perfect answer right there. That's exactly what we want to see. Traffic checks on a certain section of highway suggest that 45% of drivers are speeding there. Since 0.45 times 0.45 equals this, the multiplication rule might suggest that approximately 20% chance that two vehicles in a row are both speeding. What's wrong with this? Anyone ever been on the highway? So when you think about this, if you're on the highway and there's a traffic jam, you can't even speed. If you're on the highway on I-40 and it's like 5 p.m., as long as there's not a traffic jam, traffic might be going 75, 80, so you might be speeding because the cars around you are speeding. So let's see right here. So do we see anything that says that? The speed of two cars can have common outcomes. Disjoint is not the right word right there. There are cases when the speed of one car is not independent of the speed of another car. So the multiplication rule does not apply. So the multiplication rule, this is a big thing to know right here. The multiplication rule requires that two things are independent of each other. So they're multiplying together when they are not independent, and that's the issue. Please note the previous question went over that adding things together is the disjoint or is when they're disjoint, which is the addition rule. So these are really great questions highlighting that when things are disjoint, we can use the addition rule. Very, very important stuff right here. Oh, we did this one earlier, but we'll do it again right here. A consumer organization estimates that over a 1-year period, 16% of cars will need to be repaired once, 8% will need to be repaired twice, and 4% will need to be repaired 4 or more times. What is the probability that a chosen car will do this? And this one is talking about one car. We did another example with 2 cars earlier. Check back probably the timestamps down below to see where we did those. And let's take a look. Okay. 1684. 1684. Got it. Let's go back over here. So the probability that a car needs one repair is going to be 16%. Probability a car needs 2 repairs is 8%. Probability of 3 or more repairs is 4%. And that leaves the probability of 0 repairs to be 72%. So 72% is the remaining portion when we do 16 plus 8 plus 4. And then we subtract from 100. We get 72% as the remaining. So now we're going to use this here to solve this question. What is the probability that the car will need no repairs? We just figured that out with 72% because it's the complement of those remaining ones. What is the probability that the car will require no more than 1 repair? This is the probability of no repairs. This is the probability of 1 repairs. And we're just going to add those together because either the car needs 0 repairs or it needs 1 repairs. That's my redemption. It's one I made a mistake on last time. We're just taking these 2 probabilities because they are disjoint, because either the car needs 0 or it needs 1, and we are simply just adding those together to get the probability of 0 or 1, which is the probability of no more than 1 repair. The probability that a car will need some repairs is this. Either the car needs no repairs or it needs some repairs. So the car needs no repairs or some repairs, and we're just doing the complement of no repairs. So no repairs is 72%. I'll show it here on the screen. My Pearson's going to go crazy. So this is the probability of no repairs, which we're not interested in. And here's the probability of some repairs. And this whole thing has to equal up to 1. And now we get to a more difficult version of this question with 2 cars. 2 cars. Erase all that right there. So with the 2 cars, it is a more difficult version. And let's take a look at it. So now we have 16%, 5, and 2. So let's go ahead and write those down real quick. 16%, 5%, and 16%, 5%, and 2%. And now we have 77% right here. Double check your math as per usual. You make a mistake here, whole problem goes away. There we go. We subtract from 100. Sure. There we go. We got it right. And now when we take a look at this right here, the question asks us the probability that neither of your cars. So let me explain what this question is asking. You have two cars right now. You have two cars, and either your first car will need repairs, or your second car will need repairs, or some combination of needing repairs, not needing repairs. So if we label all the things that can occur, let's go over here to the side and put no repair, no repair. That means your first car did not need repairs, and your second car did not need repairs. Next, you could have repairs on the first cars, no repairs on the second car. No repairs on the first car, repairs on the second car. Repairs on the first car and repairs on the second car. These are all the situations that can occur. So I think the first one asks, what's the probability that neither of your cars need repairs? And this would just be this scenario right here, which is no repairs times no repairs. And no repairs is this probability right here. But since it's 2 times, we have to do 0.77 times 0.77. That's the probability of your first car not needing repairs and your second car not needing repairs. So that gives us the probability right here. 0.77 times 0.77, and there it is right there. Now, the probability that both cars will need repair, let's go back and look at our sheet where we're doing the work at. And this is the probability both cars will need repairs, but we need to figure out the probabilities of getting repairs, which is going to be this right here. That's the probability of getting some sort of repair on the car, because we're just adding them together. Either your car needs 1 repair, 2 repair, or 3 more repairs in a year. And now we need to go down here. We'll erase some of our work. And let's go right here and solve this one, because this is your car needs 2 repairs, or both your cars need repair. First car needs repair and second car needs repair. There we go. That's got it. First car needed repair and second car needed repair. So 0.23 times 0.23. And there's that probability. The last one seems way harder than it is, but we can do it with a trick. Because what we want to find for the last one is going to be the probability that at least one of your cars needs repairs. So we want to find the probability of this. But we don't want to find the probability of this. So the one I just erased right there, I kind of redded it out. It was the one where neither of our cars needed repairs. So think about this. All of this right here is the sample space, which has a probability of 1. So this has a probability of 1. It's everything that can occur. Either none of our cars need repairs, one of our cars needs repairs, repair, no repair, no repair, repair, or both of our cars need repairs. So what could we do? We could just do 1 minus the probability of no repair, no repair. And that'll equal up to this area right here, because we're just subtracting off from it the one we don't care about. That one's getting removed out of it. So we already have the probability of both cars not needing repairs, and the probability of both cars not needing repairs is this one right here. And there it is. Copy it, paste it, and we got it. That's how we do that one. You purchase a 5-pack of light bulbs. You got just enough time to do this one right here. This is a very similar problem, but just doing it in one step. And we have 9% of the light bulbs did not work. So because that's what the statistics are on it, apparently, what's the probability that at least one of your light bulbs is defective in this 5-pack? So you buy a 5-pack of light bulbs, which say 9% of our light bulbs don't work. What's the probability that at least one of your light bulbs is defective? So let's go ahead and write down what we know. We have right here that we have the probability of a defective light bulb. Probability defective is equal to 9%. Probability working light bulb is equal to 91%. So we have the possibilities listed out that you could have 0 light bulbs defective, 1, 2, 3, 4, 5, or 6 light bulbs defective. So these are the things that can occur right here. You could have 0 light bulbs defective, 1, 2, 3, 4, 5, or 6. They're perfect. So when we think about this, we want to ask ourselves, we want to see the probability that at least 1 light bulb is defective. So we are interested in this right here, meaning at least 1 light bulb in our pack was defective. We are not interested in 0 light bulbs defective. This follows the same trick that this whole area right here is 100%. This is everything that could occur. And then we want to subtract off of it the probability of 0 light bulbs defective. So what does it mean to have 0 light bulbs defective? Well, 1 minus the probability, all good. Because if 0 light bulbs are defective, they're all good. What does all good light bulbs mean? All good light bulbs means, so this would be 1 minus the probability. Well, we're not going to write probability anymore. 1 minus, all of them are good, so 0.91 to the 6th power. The reason it's 0.91 to the 6th power is because the first light bulb was good, and the second light bulb was good, and the third light bulb was good, and the fourth light bulb was good, fifth light bulb was good, and the sixth light bulb was good. I'm not talking about this number sequence here. This represents we had no bad light bulbs. This represents all bad light bulbs. So this is, when I'm looking at this, the probability of getting 0 bad light bulbs would be, let me show you right here. Probability of 0 bad light bulbs is this, and we are subtracting it from 1. We are subtracting it off of this number line right here, because the probability of 0 bad light bulbs is this probability here, and then we're taking it out of all the things that could occur. We could get 0 bad light bulbs, 1 bad light bulb, 2 bad light bulbs, or 3 bad light bulbs, or 4 or 5 or 6 bad light bulbs. And so now we just need to figure it out. We need to solve the math. Let's do it. 0.91, 2, 3, 4, 5, 6. There we go. 1 minus. And there's the probability. That's got it. Just solve the math. Oh, we got to do decimals. There we go. Oh, what? Was it a 5-pack? It's a 5-pack. Oh my gosh, I went way too quick. You know how you solve the 5-pack one? Let me go here. Someone's going to be watching this and be like, it's a 5-pack. No, it's a 5-pack now. That's how you solve the 5-pack one. Went way too quick at the end of the speed run here. 0.91 times 2, 3, 3, 4, 5. I'm going to double check that. Can't get it wrong twice. 2, 3, 4, 5. Got it. There we go. And double checking my ideas. Everything seems to be right. There we go. Everyone gets one mistake. Everyone gets one. Read 5-pack, read 6-pack the wrong way, and you do the math wrong. So you can see all that changed right here is I changed what power I'm raising it to, because this would be all 5 light bulbs are bad. That's got it. A lot of 201 work today. We did the whole homework, talked through it, and talked through the theory on it. We'll be teaching the theory today in class. But check out this video. I'll be seeing people in class soon. If you're still here, bye everybody. Bye for now. Bye.